Hola! So we are going to be talking about evolution of populations, which is going to be chapter 23. 23 in Campbell Biology 23. Sharing my iPad. Hey, come on, Gina. All right, so we are talking about chapter 23. This is all about the evolution of populations. And I'm going to break this into a couple mini ones. All right. So Mr. Anderson has some great short videos on genetic drift and Hardy-Weinberg equation, not to be confused with Harvey Weinstein. Harvey Weinstein, bad. Hardy-Weinberg, good. All right. So I love this cartoon. It's a little beaver saying like, hey, now that's what I'm talking about, because his little arm has evolved into a chainsaw. And I want to point out that natural selection does not grant organisms what they need or what they want. All right. Natural selection selects for things that are already in the population that are a result of random mutation. All right. There's a big misconception out there that natural selection works on what we want them to work on, which is just or not the case. All right. So natural selection cannot fashion a perfect organism. All right. Selection only acts on existing variations within the population. Those variations are due to random mutation. All right. And they already have to be in the population. So natural selection favors only the fittest phenotypes, which are currently in the population. And when I mean fittest, I mean survival and babies, reproduction. That's what natural selection is all about. Second thing, evolution is limited by historical constraints. So natural selection operates on the traits an organism already has, and that was dictated by by that organism's parents, which were dictated by their parents, which were dictated by their parents. Right? Adaptations are often compromises. So an example of that is when a frog gets a random mutation that makes it much, much louder than the other frogs, making it more able to attract mates. So more reproduction, however, also more attracts predators. So often adaptations are either good for part of that organism's life, but then they're a compromise, right? And then the last thing is that what we're going to see in this chapter in particular is that chance, natural selection, and the environment all interact, or they're playing a part together. So chance events like natural disasters or a changing environment, which our environment is changing rapidly right now, can affect allele frequencies. All right. And allele frequencies, changes in allele frequency, that really describes microevolution. All right. And we'll look at that in more carefully throughout this. All right. So evolution of populations, the key points. 1, genetic variation makes evolution possible. So where do we get that genetic variation? So we've already talked about random mutation being a huge part. Oh my, am I recording this? Oh, thank God. Okay. Random mutation. We have also talked about during meiosis, we know that there are 3 ways that you can increase genetic variation. 1, crossing over, right? 2, independent assortment, or how those homologous chromosomes line up next to each other. And 3, random fertilization. So sexually reproducing organisms already have increased genetic variation, but random mutation also is a big form of this. So evolution relies on this genetic variation within a population. 2, population's gene pool is defined by its allele frequencies. So we're going to be dealing a lot with calculating allele frequencies. In other words, Here, actually, I'm going to put that down here. What is the percent of big A's versus the percent of little a's for a particular gene? Those are kind of the allele frequencies. And then 3, the Hardy-Weinberg theorem describes a non-evolving population, right? Non-evolving population. And using that Hardy-Weinberg theorem, we can ask, do allele frequencies change? If so, what is the cause? In other words, is that population evolving? All right, so again, reminder, natural selection acts on individuals in a population, right? Individuals are either better adapted or worse adapted for their environment, right? However, only populations can evolve. Only populations can evolve, but natural selection acts on individuals. All right, so here are some just definitions that we need to know. The first one here is species. So a species is a group of individuals who can interbreed in nature to produce fertile offspring, right? So this is not something artificial where we put a wolf from the Eastern population and a wolf from the Western population, and if they make a fertile offspring, they're species. No, they have to be interbreeding in nature to produce fertile offspring. In other words, offspring that can then have babies as well. Second definition is population. A population can be defined as a localized group of individuals of the same species, all right? Localized group of the same species. These may be isolated from other populations of the same species. So for example, here we have the Western deer population. In here we have the Eastern deer population. If there was no pass, there would be no mixing, and those would be completely 2 different populations. In other chapters, we're going to talk about how interbreeding between those might lead to new species. The third definition is called a gene pool. And this is all of the genes in a population at any time. And remember, when we're talking about a gene, every gene, we have 2 copies, right? Or 2 alleles. For example, you can be homozygous dominant, you can be heterozygous, or you can be homozygous recessive. So there's 3 possibilities for every gene. The gene pool, you're going to throw every single allele in there. So you're kind of mixing all your alleles, all your copies of every gene together, right? All the genes in a population at one time. All right, so let's take this very small example of 3 little flowers, right? They're very small population. And luckily, I tell you here what the genotype is, right? So for any single population, we are going to be responsible for determining the genotype frequency. So the genotype frequency here would be 1/3 homozygous dominant, 1/3 heterozygous, and 1/3 homozygous recessive. We can also determine phenotype frequency. So purple would be 2/3 and white would be 1/3. And then we can figure out allele frequencies. This is something new that we haven't done before. Allele frequencies, first you have to make a gene pool, right? So the gene pool is every single allele in that population for that particular gene. So allele frequency then, we're going to take, for the frequency of an allele, we are going to take the number of that allele in the population over the total number of alleles. So if we wanted to do it for big W, we would see we have 1, 2, 3 over 1, 2, 3, 4, 5, 6 over a total of 6. If we wanted to do it for little w, we would count up the little w's in the population and put it over the total number of alleles. All right. So here we have equal frequencies of the dominant and the recessive allele. And what you'll notice, hopefully, is that those, when you add them together, are always going to equal 1. So the dominant allele plus the recessive allele is always going to equal 1. All right. And what we're going to see is that the dominant allele, we're going to be calling that P. And the recessive allele, we're going to be calling that Q. So P plus Q is always going to be equal to 1. All right, so let's look at a larger population of flowers. So here we have 9 flowers, and we're going to go ahead and figure out the genotype frequency, phenotype frequency, and allele frequency. So the genotype frequency, I always like to start with the recessive, because sometimes we're not going to know if a purple flower, for example, is heterozygous or homozygous dominant. Right? Here we do, but we might not always. So I always like to start with the recessive. So here we know that there are, the genotype, we have 2 fully recessive alleles, right? So the genotype frequency for this would be 2/9. For heterozygous, you can see we only have 1, that would be 1/9. And for the homozygous dominant, we have 1, 2, 3, 4, 5, 6. So that would be 6/9. When we look at phenotype frequency, this one's easy. We can just see it, right? So we have 1, 2, 3, 4, 5, 6, 7 of 9 that are purple. And we have 2 of 9 that are white. Now, allele frequencies, all right? So again, when I'm going to be calculating big W, I'm going to count every big W in the population. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I'm going to have 13 over, and if you're not sure how we're going to get the total is going to be the number times 2, right? The number of individuals. So we're going to have 13 over 18, because remember, we have 2 copies per. For the little w, we're going to see we have 1, 2, 3 little w's over the total, which is 18. Did I do that right? 1, 2, oops, I counted wrong. 1, 2, 3, 4, 5. Let me change that for you. So that'll be 5/18. So here for big W or P, that's going to be 13 over 18. And for little w, it's going to be 5 over 18. And what you should notice is when you add P and Q together, that's always going to equal 1. Okay? So again, by convention, when there are 2 alleles of a gene, which is most of the time, then the frequencies of the dominant allele P and the recessive allele Q are going to add up to be 1. So let's try a bigger population. So here we're dealing with a population of 3 flowers, or sorry, not 3 flowers. We have lots of plants here, right? So the first thing I like to do is see how many total we have. So this should be a total of 500 plants or 500 flowers, right? And that will help us when we do these, okay? I did my math right there, right? Okay, so I think the easiest one to start with is our phenotype frequency. All right, so the phenotype frequency, again, I always like to, so we have either pink, or white. So for the pink flowers, we have 320 plus 160, right? So 320 plus 160 is 480, right? 480 over 500. And for frequencies, we really want to calculate those out to give us the decimal, 0.96 for the purple. And for the white, we could just do 1 minus that, right? But if we wanted to calculate that out, it would be 20 over our 500. So 20 over 500 gives us 0.04. So those are the phenotype frequencies. Now let's go ahead and do our genotype frequencies. So here we have 3 different genotypes: homozygous dominant, het, and homozygous recessive, right? So for this, we're just going to take 320 over our 500, which is 0.64. For our het, it's going to be 160 over 500, which is 0.32. And then we have 20 over 500, which is 0.04. Right? So those are our genotype frequencies. Now we're going to do our allele frequencies. So remember, for our allele frequencies, we're going to have our dominant allele A, which is going to be P, and our recessive allele little a, which is going to be Q. All right. So for our big A, we're going to have, oh, actually, I'm going to always start with my recessive. I always start with my recessive. All right. So for little a, we have 20 little a, right, which is a total of 20 times 2 gives us 40, right? But then we also have 160 that also have a little a. We're not going to multiply that by 2. We're going to have 160 times 1 there because there's only one of them, right? And then we're going to add those together. So so that's obviously 1. That's 200. Sorry. Struggling on my math here. All right. So we have little a is going to be 200 over the total. Remember, the total is 500 times 2, or 1,000, because we're dealing with the alleles, right? And this would then be 0.2. So Q is equal to 0.2. So what's an easy way to figure out P? An easy way to figure out P is 1 minus 0.2 is going to be 0.8, which is what we think P is. But let's double check. So for P, we're going to have, we have 320, big A. So that's going to be 320 times 2. We have 160 of a het. So that's going to be 160 times 1, right? So we have 640 plus 160, which is 800. So big A is going to be 800 over 1,000, which does in fact give us our 0.8. All right. All right. So populations, I just want to remind you that populations, not individuals, change over generations. All right. Individuals cannot change, cannot evolve, but populations can. So I just want to show you an example here. So here we have our original population, and then we have a new generation. So what happened over time? So what we see is that in this original generation, we see 1, 2, 3, 4, 5, 6, 7. So we have 7 purple plants versus 2 white. And in this new generation, we see that the phenotypes are fundamentally different. If we go ahead and calculate the allele frequencies, right, our dominant and recessive alleles, we see that they have fundamentally changed over time, right? So we're looking at the full gene pool. We're not looking at an individual. So if we have allele frequencies that change over time, that is defined as microevolution. All right. So next time we're going to talk about all the different causes of microevolution, but I want to define it here. Microevolution is the change in allele frequencies in a population over generations. So we're really talking about the change in the dominant allele frequency and the recessive allele frequency. All right, and we'll stop there. And bye, ciao, peace.